So according to Mars, 10% of any bag of M&Ms should be blue. Right? Blue. So Mars, I think they spell it with a Z, don't they? I don't know. Mars Inc. claims 10% of plain M&Ms are blue. Gary found 16 out of 54 were blue. Is this unusual? Discuss. All right. Is this unusual? Anybody have a gut reaction to that? That's triple what they'd usually find, right? 16 out of 54 is like almost 30%. Okay, that seems a little high. Okay, so then the question, so it seems a little high. So is it unusually high then? We have to back that up with a calculation. Okay, so find a calculation to back that up. I'm going to draw a picture. Now, although I do on the test, I'm going to require that anytime we use a normal distribution, you draw a picture. This is not a normal distribution. This is a binomial distribution. You don't need to draw those. On at least one question, I will draw it for you. And I use a program called GeoGebra to draw binomial distributions, because I can just go in there and type binomial. And I want option 2. Number of trials was 54 M&Ms were sampled. Probability of a success according to Mars should be 0.1. Enter. Here's that distribution. Let's blow it up for the audience. And let's see, I do have voice, right? Okay, I have voice and video. That's the distribution. According to this distribution, options, font size 24, what is, just looking at the distribution, can you tell what's expected in a bag of 54 for blue M&Ms? Was it Stephen? 5, yeah, 5 goes with the highest stack, so 5 should be roughly the expected value. How do we calculate expected value for binomial distribution? N times P, okay. So 10% of 54 is 5.4, which means I expect to find 5 or 6 blue M&Ms in a bag on average. Might some bags be smaller than that? Might some be larger? Yeah, I found 16. That's a wee bit larger. 16 is out here in the tail. Is the stack by 16 very high? Okay, so then now we got to figure out what calculation are we going to do to determine if that is unusually large. Okay, so just check some stuff here. 16 out of 54 is approximately, what'd you get, Josh, there for the percentage? About, let's just call it about 30%. My mom would like that. Okay, that seems high. The distribution from 0 to 54 has the highest point way over here at 5, and so it's high there, and then it drops off rapidly and is very low out in the tail here. I found 16, which is right there, so I need to figure out what is the probability of getting 16 or more. I need that tail probability. Does the calculator have a button for right tails for binomials? No, it only has left tails. So the calculator could tell me what is the probability of getting 15 or less. So what would I do with that probability once I calculate it to get my right tail? Yeah, subtract it for 1. So if I do 1 minus the left tail, that will give me the right tail. That make sense? So let's figure that out. So on the calculator, I need to know what is the probability that x is greater than or equal to 16. If it's unusual, what will that number be less than? 5%. Remember the 5% rule for unusually large and unusually small? To calculate that, I want 1 minus the probability that x is less than or equal to 15. which means in the calculator I'm going to plug in the binom CDF, CDF of N 54, P 0.1, and X is 15, and I want 1 minus that. Anyone whip that out? Yeah, so I want to remove all the numbers up to 15, which should leave 16 and greater. What'd you get, Lewis? 0.005%. That is definitely less than 5%, right? Anyone else back that up? So it should be 0.00005-ish, right? Make that a percent by shifting the decimal place twice. Okay, this is an unusually low probability. Right? It's wicked small. So I got a rare bag of M&Ms. I should save that. Put it away for my kids in the future. It might be worth something, right? Okay, so this is rare. This is rare to find 16 or more blue M&Ms in a bag of 54. So that would be my conclusion right there. Getting 16 or more blue M&Ms is unusual if I'm expecting 10%, about 5 out of 54. What would usual look like? So yeah, good question. What if, well, let me see if I have some other data here. Let me look it up. I was typing in my data last night and this morning in my drive. Hopefully it actually uploaded properly. M&Ms. Sheet 2, where are you, sheet 2? Yeah, most of this data here is from the crazy guy that measured, he actually did plain peanut and peanut butter, and so altogether he did like 870 M&Ms, and he weighed and measured average diameter of every single one. So apparently he's not married, doesn't have a girlfriend, no kids. I thought I had issues. Okay, so according to my data here, blue is this column. Oh, interesting. In one bag I had 9, 13, 16, 16, and 11. So let's take the lowest one, 9 out of 58 M&Ms. So let's see if that is usual or unusual. So what about 9 out of 58? Is that usual, unusual, somewhere in the middle? That's kind of confusing. See, what is 9 out of 58 as a decimal? So we could say it's like 15.5%. Okay. Mars claims I should expect 10. Is that higher or lower than 10? It's higher, right? So that's higher. Then the question is it unusually higher? To answer that question, we have to look at the tail. So out of 58 M&Ms, about how many do I expect to be blue? If I go from 0 to 58. What would I expect? This is what actually happened, right? Mars says expect 10%. What's 10% of 58? 5.8, maybe 6. So I would expect on average I should find about 6. That should be the high point of my stack. I found 9. 9 is somewhere over here. So to see if this is unusual, I need to calculate this tail. So I need to know what is the probability that X, the number of blue M&Ms, is greater than or equal to 9. That came out weird. Which means I have to do 1 minus a left tail to check that out. So if I go to Mars's claim, so Mars, I think an S is there. Mars claims 10% blue. I wanted to know, what do I expect to get? So what's my expected value for blue? And expected value is the mean, and mean here is 10% times how many, which is 58, which equals 5.8, and I rounded that up to 6. I would expect to get about 6 if 10% is correct. All right. So our calculation is going to be 1 minus the binomial CDF or PDF here? CDF, because I'm doing a tail, and I'm removing the left tail. I want 9 and greater, so that means I need to remove up to 8. So I have 58 in this bag. Probability of a blue, that's a success, is 0.1, and I want to remove 0 through 8 possibilities. What is that? That's straight, 0.12? Okay, so it would be like 12%, right? So that's about 12%. So about 12% of the time, I should expect to get 9 or more. Is that an unusually small probability? No, a small probability would be like less than 5%. That's greater than 5%. So no, it's not unusual to get 9 or more. This is okay. This is okay. So if Mars does aim for 10% blue, then I can say that getting 9 or more blue out of 58 is not unusual. And we have the calculation to back us up on that. Because it's greater than 5%. Yeah, so if something's unusual, what we want to have happen is we want the tail probability to be wicked small. And our definition of wicked small is smaller than 5 for now. It's not an unusual, so here's the thing. So the question is 9 an unusually large number of blue? Is 9 an unusually high number of blue M&Ms? Okay, and my answer is no, because the probability of 9 or more is like 12%. That's not a small probability. It could be 90%, it could be 80%, it just depends. Yeah, so let's do one more of these, and then we're going to try a different problem. Suppose I found a bag, and I'm looking at blue again, blue. Suppose I found 5 out of 55 were blue. Okay. According to Mars, I expect about 10% of 55. So the expected value here is 5.5. Now, you might say I can't have half an M&M, but that's not true. In one of my bags, I had 4.5 orange. One was almost exactly cut in half. All right. So I kind of can, but usually we would say, because they're whole objects, 5 or 6, that means. So did I get what was expected? Okay, so it shouldn't be unusual. Okay, now let's look at it this way. Is 5 out of 55 above or below the mean? It's below the mean. So then I would ask the question, is this unusually low? Okay, so since 5 is less than the mean, 5.5, it's smaller. Is it unusually small? So you just kind of happen to end up above or below the mean. It just depends on what you find in the data. You never know what's going to happen. In this case, we ended up below the mean. So that am I doing a left tail or a right tail in this case? I'm doing a left tail this time, yeah. Oops, sorry about my crazy pen. I need to order a new one. I think this one's probably the edge of its lifespan. So here's my distribution. It is skewed wicked to the right or left. Left, the tail is the skew. Yeah. So I found a mean of 5.5. That's theoretical. Experimentally, I found I had exactly 5 blue M&Ms. So if 5 is unusually small, then this tail probability will be small. So that means I need to calculate the probability that x is less than or equal to 5, which is just a straight binomial CDF, where n is 55, p is 10%, 0.1, and x is 5. Anybody got a number on that? So 52.4%. So what that means is if I take a whole bunch of bags of M&Ms that happen to have 55 in them, I would expect about 52.5% of the time they will have 5 or less M&Ms, 5 or less blue M&Ms in them. So if I had 1,000 bags of M&Ms that all had 55 M&Ms, about 524 of them would have 0, 1, 2, 3, 4, or 5 M&Ms in them, is what that tells me. Exactly 524 of the bags? No. Somewhere in there. Law of large numbers. 1,000 might not be enough. Okay. How are we doing? Getting better on the unusually large and unusually small? All right. So I've got a new problem for you. Let's take a spreadsheet problem, and you're going to try and do it on your calculator. Yeah, so here's the deal. If an event is unusual, if its tail is smaller than 5%. So we found the tail has 52.4, which is common. So it's not at all unusual. It's very common to have 5 or less M&Ms in a bag of 5 or less blue ones in a bag of. I guess I should write that down. So it is quite common. Hang on a sec. To get 5 or less blue out of 55 if 10% blue is expected. That's my conclusion on that. So quite common. Would you guys agree that is definitely not unusual? Right, so you could say not unusual instead, but I decided to write the phrase quite common. Yeah. Yeah. I did the PDF on there because I wanted to see what was the probability of getting 16, which isn't really relevant, but I calculated everything I could on that problem. So sometimes I whip out all of my guns, and then I say, okay, which ones of these actually killed it, right? So the only thing I really need to solve that problem is the binomial CDF to find a tail. However, if I don't know whether to ask if it's unusually high or unusually small, what other calculation do I have to do? Right? Some problems I'll just say, is this unusually small? But what if I just say it's unusual? Then you don't know if I mean small or large. How do you determine which to go for? You could do both, okay, but there's another way to check before bothering to do both. What calculation did I do here that's significant? I did the expected value. Yeah, I saw what was expected. If I'm below what's expected, that means I'm checking for unusually low. If I get above what's expected, then I check for unusually high. Because the mean is what should happen on average if you repeat this a whole bunch of times. Okay, so the mean tells you whether something is unusually is high or low. The CDF tells you if it's unusual, high or low. Okay. All right, we are going to try a new problem. I'm going to put something here. I need to increase the font size. Let's try 24. Come on, nothing happened. All right, so X, 0, 1, 2, 3, 4, or 5. Probability of X happening is going to be equal to binomial, dist, I guess, number of successes, that is X. Probability, let's go with 0.3. And total number of trials is 5. And I want cumulative is false. Oops, can't spell false.
Why do you put the false in there?
Oh, I did something wrong. So on the spreadsheet, it wants to know whether it's cumulative or not. Cumulative means add up everything up to that point. So that would be true. If you just want a single probability, then that means cumulative is false. You only want the single probability. And Excel does it that way, and pretty much every spreadsheet does it that way. Instead of having two formulas, a PDF and a CDF, they have a single formula with the true or false option. And there's a lot of different probabilities that happens for. What didn't it like? It didn't like the way I typed false, maybe? Does it have to be capital false? Maybe. Maybe. No, it says there's an error. Error. Binomial distribution parameter 3 value is 5. Valid numbers are 0 through 1. Oh, I entered things in the wrong sequence. Darn it. I didn't want to do that. Okay, what's next? Oh, number of trials is 5. I had them in the wrong order. And then 0.3, and then false. Okay. So here's what I want you to do. Here is what I claim is a probability distribution. Could I be wrong? How could you check to see if something's truly a probability distribution? Add the probabilities. What do they have to add up to? Yeah, so those better add up to 1. Now don't bother doing that by hand. Here's what I really want you to do. I want you to enter the X's in list 1 on your calculator, and I want you to enter the P's in list 2 on your calculator. And then you're going to run one variable statistics on that. And it will do all the calculations you need. You will need to do this on the test. So let's practice it. This is the question Michelle asked about 5.2, mean and standard deviation for a probability distribution. Okay. You can't read those numbers? Let me blow them up some more. Let's see, font size, let's try 36. How's that? Better? Okay, list 1 and list 2 on your calculator. I'm going to get my calculator warmed up here. And we're going to run the one variable statistics on that. Hey, just looking at my table, can you guess what the mean might be? Just looking at my table? Which has the highest probability? 1. So the mean is going to be close to 1. Yeah. Oh, postpone. Okay, hopefully I typed them correctly. I think I did. Calculator says the mean is 1.5. Calculator says the standard deviation is about 1.02-ish, and n equals 1. Here, when you do a probability distribution, n is your sum of your probabilities. Okay, so that's appropriate. My frequencies do add up to 1. Okay, so I do have a probability distribution. This happens to be a binomial distribution. Did you notice when I was typing that formula? I chose p to be 30% and n to be 5. What's 30% of 5? What's 30% of 5? 1.5. What's the mean here? 1.5. Yeah. Mean of a binomial distribution is the total number of trials times the probability of a success in any one trial. And I was aiming for the probability of a success to be 30%. Did I achieve that aim? Yes, I did. Okay. So let's answer a couple of questions here. Can you calculate for me what number is 2 standard deviations below the mean and what number is 2 standard deviations above the mean? Whoa. What's 2 standard deviations below and what is 2 standard deviations above the mean? Oops. So we have mu is 1.5. Oops, 5. And where should I round the standard deviation to? What's the rule for that? What's that? Not necessarily. 1 decimal place more than the data. Okay, what the hell is my data here? Which column represents the data? The X's represent the data. My data could be 0, 1, 2, 3, 4, or 5. So what this could be data for is Gary gets to take 5 free throws. Probability he gets it in is 30%. Ah, shit, I missed. What's the probability he gets exactly 1 out of 5? About 36%. What's the probability he gets exactly 2 out of 5? What's the probability he gets at least 2? At least 2. So what are possibilities for at least 2? 2, 0, or 1? Yeah, so if I add up these 3, so 30%, 16%, 17%, that's what, 60, 70, 80, 3-ish? Something like that? Right, rough ballpark, right? 30, 83, about 83% chance of getting 0, 1, 2, or 3, 0, 1, or 2 in. That's what the table is telling me. I can answer all kinds of questions like that. Since I know that this is binomial, n is 5, and p is 0.3, since I know that now, I could also use the binomial CDF to answer that question, aside from using the table. There will be a question like this on the test where I'll give you a binomial problem. I'll also give you all the probabilities in a table. I'll probably draw a picture of the histogram, and I'll just ask you to answer a few questions about it, like we're doing now. So I would say rounding the standard deviation to the nearest tenth would be 1.0, right? So 2 standard deviations below the mean, mu minus 2 sigma, would be negative 0.5, right? 1.5 minus 1 again. Is that right? I think so. Yeah. 2 standard deviations above the mean, 3.5. Okay. So now I want to see what is the probability of getting a number between negative 0.5 and 3.5. So that means I want 0, 1, 2, 3. Do I want 4? No, it's too big. Do I really want 3? Is 3 within inside that interval of numbers? Yeah, it's smaller than 3.5. So that means I want to add up these 3 probabilities right there. So I want to know what is the probability that the number of free throws Gary gets in when he throws 5 is within 2 standard deviations of the mean. Okay. So in this case, that's the probability of getting 0, 1, 2, or 3. Since I happen to go from 0 all the way up, this coincidentally is a CDF problem. It doesn't always work out that way. So you can either add those 3 numbers together or try a binomial CDF, see what you get. What is the probability that I get a number within 2 standard deviations of the mean? Come up with a number. I'm going to come up with a number, and hopefully we get a similar number. Google Drive says 96.9% roughly. If I were to do a CDF calculation, that would be number of successes is up to 3, number of trials is 5, probability of success is 0.3, and this is true for cumulative. So if you did the CDF on the calculator, you should get exactly the same number. Okay, so I'm going to do the calculator next to confirm that I'm not full of shit. Everyone paying attention? So let's see, where do I find the binomial CDF again? Second vars, right, distributions. So on a test, I couldn't answer the question, should I use the binomial CDF here? That would be inappropriate. But I could answer the question, where the hell is that button on the calculator? Okay. CDF, so trials is 5, probability of a success is 0.3. I want to go up to 3. Calculator says 96.922, same thing as Google Drive said. Okay. So I did 3 different ways, I got the same number. All right. What's the range rule of thumb say? Doesn't the range rule of thumb say within 2 standard deviations of the mean you should expect a certain percentage of the data to be? I calculated 96.9. Range rule of thumb says what? Empirical rule says what? 95%. Oh, good, you're scaring me. 95% is what the empirical rule says. Now, the empirical rule applies to what kind of distribution? Is this a normal distribution? No. Binomials can be approximately normal if the probability of a success is close to 0.5. 0.3 really isn't close to 0.5. But here, 96.9 is not too far away from 95%, right? So it's kind of relatively sort of normal. Do you want to see what the distribution looks like? To see the distribution here, I could do a histogram on this, I think. Oh, I wonder if the calculator can handle a histogram on those numbers. Let's try. Stat plot, enter. You will not need to do a histogram on the test, but you can always do one if you want. I think it might freak out on this data, but maybe not. Oops, wrong button. Zoom 9. Ooh. Damn, I got a graph on there too. Let's turn off that graph. Oh, calculator was not happy about that. Clear, clear. I'm going to pick the window for it. Let's see, I want to go from 0 to 6, scale by 1. Ymin should be 0. Ymax should be 0.5 should work. Oh, no, it did it. Cool. Calculator can do histograms that are probability distributions. That's kind of nice. So I got the probability of 0, 1, 2, 3, 4, and 5 is too small to see on the graph. That's kind of nice. On the test, I will give you that picture for one of the problems to answer questions on. Okay, so everyone cool on? So if I give you a probability distribution like this right here, and I ask you to find the mean and the standard deviation, are you going to do it by hand? I wouldn't. I would use the calculator if I were you. How do we use the calculator? Yeah, second variables. No. Let's go back. One variable statistics. Yeah. So you go to stat, calculate, one variable statistics. That's how you find the mean and standard deviation of a frequency list. No, it's just stat, one variable statistics, no second. You write what you do, yes. So if you use the calculator for something, then what I'd be expecting to see for like this right here is that you went to stat 1 var stat list 1 comma list 2. So this is what generated my mean and my standard deviation. Yeah. The bigger thing I really need it for is anytime you do a binomial calculation or a normal calculation. That's where I really need to see it, to make sure you pick the right one and put in the right numbers. Okay. So let's do a normal problem. So I am going to pick on the M&M problems. Postpone. Yep. It's a good question. Let's take a look at the sample test. For normal, no. For binomial, maybe.
Yeah, that's fine.
Yeah. All right, so let's see. Doc sharing, I got a few tests here. Let's take a look at Gary's sample exam 2. This is the longer of the two. This is at least 50% longer than what I would give you in class, just to give you more practice. Okay, so just a quick scan of this here. Viagra was used. 17% of the patients had headaches. 117 had headaches. 617 did not. What's the probability of Viagra user had a headache? That's just a straight probability. You take 117 divided by, now this is headache or not, so you have to add those up to get the total. Okay, so that's just a straight probability question. No fancy formulas at all. Next one, I say probability that a girl is born is about 57% due to toxins in the water. Once I give you a percentage like that, it's probably a binomial problem. So the key to, it's not responding. So if I give you the percent of something happening, like the percent probability of a success, having a girl, having green peas, finding blue M&Ms, those are binomial problems. Okay. As far as binomial goes, so let's write this down. So the key to finding whether something's binomial, key for binomial, is a percent success will be given. Okay. So I might not use the word success. I might say the probability of having a girl is 57%. So since I'm focusing on girls, having a girl would be a success. Sometimes the word actually success will be in there, but not always. But a percentage will be given. So that means it's probably binomial. As far as the binomial PDF, that means you're finding a probability of a single number. Like, what's the probability of getting 4 out of 7 girls? What's the probability of getting 2 out of 5 girls? Yeah. So example As far as the binomial CDF goes, oops, it's not the whole word, binom CDF, that's the probability of a left tail. So probability of a number or fewer. Yeah, so what's the probability I get at least 3 in, right? That means at least 3 is 0, 1, 2, or 3. Yeah, so you know, algebraically, it's something like, what's the probability that x is less than or equal to 3? In words, it might be the probability that x is at least, no shit, that's wrong, at most, is at most. Okay, so I was playing basketball, I got at most 3 out of 10 in. You gonna pick me for your basketball team? Probably not, right? If you're a better shot, probably not. I'm gonna be a bench warmer, yeah. And so again, important thing about the CDF compared to the PDF, it's a left tail. CDF is a left-hand tail in a distribution. All right, so if we look at some of these other questions, probability of having a male child is 0.45. What do you think, binomial problem? No. It was found the graduation rate was 94%. Like, what's the probability somebody graduates? What kind of problem do you think that is? It's a binomial again, yeah. Whole bunch of binomial problems. Here I give you the distribution. Tom lost 56% of all hands tonight. Right, this is probability of losing. That's what we're focusing on there. Scroll down a little farther. For the standard normal distribution, is that a binomial problem? No, it says normal. Typically, the normal problems will actually say this is a normal distribution. Right? Women's heights are normally distributed. Problem 10. Normal, not binomial. Assume weights of men are normally distributed. Again, normal problem. The tricky thing about the normal problems is, do you have to use the central limit theorem? Okay, and the answer is sometimes. Blood pressures, normally distributed. So if it's normal, it'll just come out and say normally distributed. Okay. The hardest thing about the binomial problems is it just a straight probability, just do a division, or do you have to use a crazy formula? Okay. And a big hint on this one, if my real test is anything like the 2-sample test, only the first problem were straight probability, then there were a bunch of binomials, then there were a bunch of normal problems. Okay? And I try to keep them in order so as not to confuse anybody on purpose. I'm not trying to ask any trick questions. Yes, where? Taryn. Uh-huh. Yes. Yes, correct. That's a right tail, so let's put that in here. Binomial right tail. Probability that x is greater than or equal to some number like 3. That means x is at least 3. X is 3 or more, things like that. On the TI, that would have to be 1 minus the binom CDF of the left tail. So I want to keep 3 or more. What do I want to get rid of? Less than 3, what number, what's the first number less than 3? 2, so that's what I have to enter here. So let's suppose n here was 10 and p here was 0.45. Then I would enter 1 minus the binomial CDF of n, p, and then everything below 3 would be 2 and less. It would look like that. So this is 1 minus the left tail gives me the right tail. Okay. You have to decide based on keywords that you see in the problem. If you're doing 1 minus, that means you're doing a right tail. You're calculating a left tail. Yeah, so that was this example over here. Left tail. So generally, I'm in the practice of every time I do one of these problems, I draw a picture, and then I ask myself questions. Am I going to the left, or am I going to the right? And sometimes I get confused about at least or at most. Does anybody else get confused about that sometimes? So what I do is then I just imagine money. Okay, let's see. If I have at least $3, what does that mean? I have at least $3. I need lunch. I have at least $3. I can get a pretty good lunch. Okay. Then I might say, okay, what if I said that to my daughter, or she said that to me? All right, so sometimes money helps me get it straight, which is which. Sometimes pick a number and see, is 5 at least 3? It is, yeah. 5 is at least 3.
How do you figure that? I don't know what you mean by that.
Okay, so at least means the lowest number I can have is 3. So 5 is at least 3, yeah. So getting used to the language. Hopefully we're used to it by Friday. Monday, yeah. Yep, let's do that right now. So let's look at my M&M data again. Okay, so let's see. According to the data collected by this cool guy on the internet, and I don't know his name, write this down, or I'll just copy it. Let's put it in my notebook. Whoa. Okay, so according to his data, a sample of almost 300 plain M&Ms, we have a mean and standard deviation up here. Mu, sigma. Okay. Now, we got to decide how to round mu and sigma here for plain. So this is for plain M&Ms. And this is weight in grams. That's what we're playing with here. All right, so looking back at the data is to the nearest hundredth of a gram. So what should we round our mean and standard deviation to? Thousandth, yeah. So we're going to say mu is equal to 0.865, and sigma is equal to 0.61, or 0.61, sorry. 0.061. So that's going to be our mean and our standard deviation. Okay. Now that's for a single M&M. Single M&M. So I was sampling M&Ms to try and test out, compare my data to his data, and I found that in, let's see, which bag, here we go. I'll highlight that. My bag that had 16 blues that we were playing with earlier, the mean weight of a single M&M was 0.89. Let's write that down. So blue, mean weight. Actually, let's get rid of the word mean for just a minute. We'll come back to that momentarily. Go away. We're just going to say the weight of a single M&M, and I'm missing a letter there, aren't I? the weight of one M&M is 0.89 grams. What is its z-score? Oops. Nope, no charts. Okay, so you definitely need to know how to calculate a z-score. I'm not going to give you that formula on a test. So z-score is the object you're looking at. I'm looking at an M&M that weighs 0.89 grams. I need to know how far it is from the mean. The mean is 0.865. And divide by 0.061. So that is above the mean, right? So I should have a positive z-score. .89 minus 0.865, close parentheses, divide by 0.061. So about, let's see, in the book, were they taking z-scores to like 4 decimal places often, or 3? 2? I think it was 4 for percentages, maybe 2 for z-scores. I'm going to go 2. I'm going to call it 0.41. Z-score is about 0.41. So is this particular M&M more than 1 standard deviation from the mean? No, it's less than 1 standard deviation from the mean. It's 0.4 standard deviations to the right of the mean. What is a z-score? Z-score just counts standard deviations. This says we are a fraction of a z-score to the right. Okay, that's what that tells us. All right, so next thing I want to know, what is the probability that I weigh an M&M and the weight is exactly 0.89 grams? 0, thank you very much. Yeah, in a continuous distribution, the probability of any one number occurring is 0 out of, it's 0, 1 out of infinity. It's 0, because that's not a worthwhile question. I can ask a different question. I can ask, well, what's the probability that the weight is going to be heavier than 0.89 grams? Right? I like big M&Ms, more chocolate, or maybe more hard candy shell. Which is heavier, you think? Probably the hard candy shell. It's denser. Chocolate's denser? I don't know. We'll have to test that later. Oh, moisture maybe. Oh, shit, that's a tough one. But they whip chocolate, right? So it's not too brittle and hard. I don't know. That's a tough one. Okay, so we don't know that question. We're not going to answer it today. So this I can actually answer on the calculator. Let's draw a picture of this. Mean of the distribution, I believe, was what, 0.865? The number I'm questioning here is to the right or the left of the mean? To the right, because it had a positive z-score. Yeah, so if this is a z, so if a z-score of 1 is right here, so if that's 1, 2, 3, then my number must live somewhere about right there. So there's 0.89. And I want to know what's the probability it's bigger than that weight. So I need that left tail. Do a calculation. See what you get. Oh yeah, that one, right side. Yeah, sorry, I'm left and right confused. Right tail. Calculate the right tail for this normal probability. So what is the chance that I'll find an M&M in a bag that has a weight of greater than 0.89? Which formula am I going to use for this? Normal CDF, not binomial. This is normal. We're doing normal distribution. Yeah. So I was assuming that the weights of M&Ms are normally distributed. Yeah, that's why I wrote up the mean and the standard deviation there. Actually, I don't think I said that clearly in the beginning of the problem. Standard deviation is 0.061. 0.865. Oops.
Go back to, yeah.
You got the mean, standard deviation. So I predict that the answer is less than 50%. Anybody know why that's got to be a safe prediction? 50% would be right in the middle, and this is to the right of the middle, and I'm going to the right of that. So it's got to be less than 50%. I'm not sure how much less until I calculate it. Right, so what's my, oops, keep kicking the wrong button. The calculation I think I'm going to do is the normal CDF, and the normal CDF wants left, right, mean, and standard deviation. So for my left, right standard deviation, my left number is 0.89. It's supposed to be a point. Come on, point. My right number is infinity, and the calculator's closest to infinity is 1 times 10 to the 99th, which is what this means. Mean is 0.865, comma, standard deviation is 0.061. And to the nearest 100th of a percent, what is this probability? 100th of a percent, so you got to move the decimal point and then give me 2 more. 34.09? Okay, 0.096, so we'd round that to 0.10. So to the nearest 100th of a percent, it would be 34.10 is the way that would round. So 4 decimal places gives me 100th of a percent. That was given. It was given that the standard deviation was 0.61. No, the binomial can only do left tails. The normal can do left. On the calculator, the normal can do left, right, or anything in between. There's a 34% chance that you're going to find an M&M in a bag that weighs more than 0.89 grams. That's relatively likely. Okay. 34% chance that an M&M weighs more than 0.89 grams. Normal PDF does left tail, right tail, or anything in between because you can tell it what number is on the left and what number is on the right. Yeah. The binomial does not ask you for that. It only asks you to go up to a certain point. That's why we have to do the 1 minus with the binomial. The normal, though, because it takes an extra parameter, can do a variety of more calculations easier. Those of you who use spreadsheets, the spreadsheet is not this easy. It's a little harder on the spreadsheet. Okay, before you run, I got one more question for you. Now, that 0.89 was actually the average weight of my whole bag of M&Ms. How many M&Ms did I have? I had 54 M&Ms. Average weight of 54 M&Ms is the 0.89. So now I want to know, what is the probability that the mean of the weights of 54 is greater than 0.89? Is that the same calculation or is it different? Why is it different? Yeah, because I narrowed. So originally I had 54 M&Ms. I took all their information and I compressed it into a single number. When you do that, you have to also compress the standard deviation to answer the question correctly. I shrunk all of the 54 M&Ms information down to a single number. Okay, so what is my new standard deviation then? Yeah, you have to divide by the square root of the sample size if you're talking about the average of some group of numbers. That's the central limit theorem.
What is NEBS?
New, that's supposed to be new. New standard deviation, because I'm looking at the average weight of things. Formula there is you take the standard deviation of the population and divide by the square root of your sample size. You have to compress the distribution to answer the questions properly. This is called the central limit theorem. Yep. All right, make sure you check out those sample tests. There's answers for them online too. Oh yeah, if you wrote a question, please turn them in before you leave. A binomial question.
I wrote a question by email.
As long as